NMR is most well known for its use in doing these big, elaborate structure determination problems. We have all these different spectra and you piece all the little parts together and finally come up with a viable structure. That is a hell of a lot of fun to do, but let's face it, NMR has many more uses than that. And in fact, some of the most common uses of NMR, some of the most routine uses of NMR, I think, should be checking your starting materials. Whether you're a undergraduate student starting a research project for the very first time, a seasoned and experienced research scientist, or some poor schmuck with delusions of grandeur down there in hellhole Georgia, if you're going to use a molecule in a synthesis project or study its biological effects or something, then it's really a good idea before you get started to pump a little bit in an NMR tube and see if it's really what you think it is. Okay? That's basically what I mean by checking your starting materials. It is critical that you get in the habit of doing this so that if you are doing a synthesis project, you don't want to find out 3 weeks after you got started and were frustrated that your starting material was actually oxidized or the label was wrong on the bottle. And let's face it, things like that happen. Or it had a significant contaminant that you didn't know about and that was causing you trouble. So always, 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 always check your starting materials. A really good illustration of how important that is came from Chemical and Engineering News back in 2012. When they had an article on a chemotherapy reagent. It was called bosutinib. I'm not sure how the hell you pronounce it. I don't really care. But it was a potent chemotherapy agent and is object of a lot of research groups around the world studying this thing. And many of them, would simply buy bosutinib on the open market and, study the molecule and do their research with it. And it was a couple of years before this that some of these research groups were noticing some issues, some troubles that they were having difficulty placing. Sometimes in reproducing results from earlier and that kind of thing. And one of the groups did a full NMR study of their starting material and discovered that some of the batches they had bought on the open market were not correct, were the wrong isomer. This is the graphic from the article. And they highlight on the top here, this is the actual bosutinib molecule, and down below is what they believe was the false bosutinib, the incorrect isomer that was sold as genuine bosutinib by some manufacturers. And it is only in this one ring that they highlight here where in the isomer, the false material, that ring is symmetric. That would affect the number of peaks in a C13 spectrum compared to the actual molecule that people were interested in studying. Now, this is a big molecule. The NMR spectra are not going to be trivial, but if you're going to do this type of stuff, then I think it's critical that you are absolutely certain of the material that you just bought. And this is, I think, a nice illustration of it. Quoting the paper for a moment, there's a couple of sentences in here that I think are really nicely laid out, and so I want to quote these directly. The difference between the two molecules is subtle. Mass spectrometry and elemental analysis would be the same for both compounds. There are differences in the aromatic region of the proton NMR, but it's only when you do C13 NMR that the symmetrical nature of the aniline group in the isomer becomes clear. And the issue, of course, is some of the research groups that had the false bosutinib had been doing years of research before they discovered the issue. And that is just a major crisis. And so always, 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 please check your starting materials. Now, to illustrate this a little bit more, one of my colleagues here at Georgia Southern, a biochemist, a couple of years ago, wanted some help running an NMR spectrum checking a starting material. Now, the starting material was this molecule here has the acronym FMOC. I have no FMOC. I don't know. It's some organic name. Who the hell cares? But it's and I don't even, it seems to be a protecting group for an amino acid synthesis. I don't care what the biochemists use with this thing for either. Their question was, did the FMOC we buy, well, was it FMOC? Was it clean? Did it have any contaminants in it? And so, being good chemists, she and her research group wanted to get some NMR spectra of their starting material, check their starting materials before they proceeded. And I was happy to help them with it. We dissolved up about 10 milligrams of FMOC in an NMR tube. It dissolved really nicely in deuterated acetonitrile. And so, having the sample, it was off to the instrument. And so to get ourselves in the right frame of mind, to be able to look at the structure of FMOC and figure out, what we should expect to see and whether the spectra we obtain truly match FMOC or not, we're first going to do as we often do, try to relax and take a look at a picture of a cat and a horse. Now that our minds are ready to go now that our minds are clear and ready to go, I'm going to change into my more formal teaching clothes. Now that our minds are calm and at peace, we are going to, our minds are calm and at peace. Now that our minds are calm and at peace, I'm going to get myself in a proper teaching uniform, and I'm going to get my fat old ass down there on the glass, and we will analyze the spectra and the structure of this molecule. See you down there in a moment. All right, now that I have my proper teaching uniform on and down here on the glass, I can just, and we're also at a state of peace of mind, I can just feel the academics flowing through me. And so it's time to take a look at the structure of FMOC and what we would expect to see in its proton and its carbon spectra. Now, here's the structure of FMOC, and it is critical to note that it is a symmetric structure. Okay? There is a plane of symmetry right down the middle here. Some people would look at this chloroester section and say, but wait, it's over on one side of the molecule. But remember, with free rotation about that single bond, there is an orientation where this is swung around to this position. That is perfectly symmetric. Therefore, the molecule is symmetric. That is going to have a big effect on the appearance of our spectra. So we must keep that in mind. We take a quick glance at the proton spectra for a moment, and it is a very nice proton spectrum. We see lots of peaks in here. And so it's critical that a lot of times students want to just dive in and start assigning peaks left and right, and that's good, but what we're going to do is think carefully about some of the peaks that we are going to see in this molecule because of things other than FMOC, than what we expect to see from FMOC itself, and see how that matches up. The most critical thing that we need to look for are contaminant peaks and the residual solvent signal. And there's definitely going to be a residual solvent signal here. This one is run in deuterated acetonitrile. Remember, when you look at the bottle, it's going to say something like 99.9% deuterated, which is their way of saying they did a pretty good job of replacing every hydrogen with regular hydrogen with the heavy isotope of hydrogen, deuterium. But it's not perfect. It is never going to be perfect. There is always going to be, remember, a trace of CHD2CN, okay, in there. There's going to be a trace of that, just because the deuteration process is not absolutely perfect. And this proton, it's called the residual solvent peak, is going to show up. And this will be true of every single NMR solvent you use that has hydrogen in it, and that's most of them. So it's critical you know where the residual solvent peak of every solvent you use, acetonitrile, DMSO, chloroform, where are those residual solvent peaks? Now you can find them all over the place. There's a lot of references out there. This particular article, and here's the reference to it,
came out a couple of decades ago in Journal of Organic Chemistry. And what it is a compilation of a lot of work in measuring residual solvent peaks and common contaminants in in almost all of the possible solvents that you will ever see in NMR spectroscopy. For example, if we use the reference paper, it's going to tell us the residual solvent peak, this trace hydrogen sitting in our deuterated solvent, is going to show up in a proton spectrum at exactly 1.94 ppm, okay, for the protons. That is the residual solvent signal for deuterated acetonitrile. And if we look at the proton spectrum, we do see a peak at exactly that position. In fact, going close up on it, the thing is actually a glorious pentet. I look at that and I just get all happy inside when I see it. Why? That hydrogen would be a pentet. Well, that's a question for another day. But we see it in the spectrum, so when we see this little peak in our FMOC spectrum, we do not look at it and go, oh my gosh, my sample has something down here at 1.94. No, it's your residual solvent peak. The other one that we see is fairly close by is a large singlet over here, and the reference standard tells us, and this is extraordinarily common, that water in deuterated acetonitrile will come up at about 2.13 ppm. That's the water peak here. Now, water could be that a polar solvent has absorbed a little bit of water from the atmosphere. If it was used in the open atmosphere, all solvents are going to pick up a trace of water. If it had, only if it's been in a dry box under anhydrous conditions, can you avoid this sort of thing? Some samples, if they're polar molecules or hydroscopic, will pick up water out of the atmosphere. So water comes in almost every single proton NMR spectrum you run. Its position is highly variable. It can move around in a lot of different places depending upon what solvent you're dealing with and what its concentration and temperature are. This is 2.13 is about the standard position at room temperature in normal concentrations, not unusually high for acetonitrile. Now this particular sample of FMOC does have a fairly large water peak. This indicates either the solvent was wet or the sample itself brought some water into the solvent when it dissolved. But it is a wet sample. That is one thing we can take away from it. Once we have these peaks, solvent and residual solvent peak and water out of the way, and any other common contaminants, I'll talk about those a little bit later, we examine the spectrum and the structure and see if they match up. So looking at the spectrum, or looking at the structure for a moment, most obvious thing, this is an aromatic molecule. Okay? And being aromatic, it's going to have, with the symmetry, 8 hydrogens, 8 aromatic hydrogens. The chemical shift range, 7 to 8 ppm, can be a little bit lower, a little bit higher, but that's generally a good area to look for. Now, in an aromatic, they can be all jumbled together. In other words, all of these could come in kind of a messy looking pile, or they could be separate, or some combination of the two. Aromatic regions are notorious for lots of overlap and distortions and so forth. So I tend to say we're going to just see, are there peaks that integrate properly in this region? If they are separate, then we could see up to 4 peaks, okay, here. And we could even make a prediction on their coupling patterns. These two positions with only one neighbor should be 2 doublets. These two positions should be 2 triplets. This one has 2 neighboring protons nearby. Now, we may not see that level of detail. It may be all jumbled together, but this is what we're going to look for in the aromatic region. The other area, of course, is the aliphatic region. there are two protons up here. Okay? Drawing it out in a little more detail, this is a CH2, CH, and the aromatic rings, and then of course the oxygen and the rest of the molecule here. These are adjacent to each other. They're going to be coupled to each other. Looking at the CH2 group for a moment. Okay, the CH2 group, I would guess, this is chemical shift-wise, it's going to be somewhere over 4 ppm. This is right next to an oxygen of an ester. This is actually a chloroester, so that may move things up a little bit farther. So 4 to 4.5 ppm or so. It would be expectations. 2 hydrogens, it should integrate to 2, and with one neighbor, it should be a doublet. Okay, the CH. Now, this one's a little bit harder to figure out on the chemical shift. It is a proton adjacent to an aromatic ring. That brings it somewhere in the neighborhood in 2, 2.5. This one's adjacent to 2 aromatic rings. We'll move it a little bit higher because of that. It is up, near this CH2 group that is next to the ester. Myself, I'm going to give it 3.5, maybe to 4 ppm at the most, is my guess. 1 hydrogen, it should be a triplet. And that's it. There are no other protons in this molecule. The symmetry renders those two sides of the aromatic rings equivalent to each other. And so we bring up the proton spectrum one more time. And sure enough, in the aromatic region, it does integrate to a total of 8. It is actually nicely separated. Each of these peaks integrates to 2. There are 2 doublets. There are 2 triplets. Okay, nicely separated from each other here. In the aliphatic region, sure enough, we see a doublet. This one's at about 4.6 ppm. And then we see the triplet. It does integrate to 1, and it's actually a little bit higher than my back-of-the-envelope calculation told me it was going to be. It's actually around 4.2 ppm. But that's okay. I can handle that. And everything else matches up beautifully. The proton spectrum tells me the following, that this sample is almost certainly FMOC. It is not contaminated with much else. There is, however, water. That's what I take away from this. Now, I'm 99% certain that this sample is FMOC. Everything matches up nicely. But as we talked about previously, if you can do so in a relatively small amount of time, it's not a bad idea, especially if a lot's writing on this kind of research, to also do the C13 spectra of this thing. And because it will give you even more confidence in your assignments and in your knowledge that your sample is pure and ready to go. So looking at the C13s for a moment, once again, there are plenty of aromatics. Now, this one, we're going to expect to see 6 carbons in here. 4 of them CHs, 2 of them quaternary. Okay? And that they're still nice and symmetric, so there's going to be 6 of them. The chemical shifts, aromatics, tend to be 120 to 140 ppm or so. Often the CHs are a little bit more upfield, the quaternary is a little more downfield. So that's what we expect here, pretty straightforward. These two, the aliphatic carbons, the CH and the CH2. Chemical shift-wise, that's a pretty crowded region. For these, maybe 30 to around 70 ppm is the region to look for here. Like I say, a lot of stuff comes in there, so it's going to be a kind of a crowded region, not a lot distinguished here. But a distinguished one is this. There is one more carbon, didn't see it in the proton, there is no proton out there, but the carbonyl of the chloroester. Now, esters, baseline number about 160 ppm. That can vary some, but this is a good number to start with. Okay, about 160 ppm. Now, This being a chloroester, that's going to make it a little more uncertain. I'm going to put plus or minus, say, about 15 ppm in there, but we definitely need to see this carbonyl, and we need to see it somewhere, not at 210 ppm. That's more in the realm of a ketone, for example. Now, before we dive into the carbon spectrum, I do have to do one other thing. Probably should have done it before I started talking about the C13, but, you know, what the hell. And that is residual solvent peaks again. There's a trace of the hydrogen in there, but in deuterated acetonitrile, as we talked about, almost every single solvent we use outside of D2O is going to have carbons in it. These positions are about 1% C13. We're going to see them. The reference paper I mentioned earlier, so valuable for protons, is just as valuable for carbons, and it tells me that the C13 signals for acetonitrile are at 1.36 ppm. For carbon, that is, you know, pretty downfield, pretty upfield, and the other is 118 ppm. Okay, that is the nitrile carbon. Okay, so there's actually two residual solvent peaks in a solvent like this. So we take our carbon spectrum, and the first thing we do is we look for these, okay? Because, you know, before we make anything about our sample, we must see the residual solvent carbons. And in this particular sample, we do, okay? They're very lovely. 1.36 shows up very nicely. It is a marvelous, beautiful, almost heartbreakingly beautiful septet, and the nitrile carbon shows up very nicely as well. We make note of these right on the spectrum or something, that this is the solvent. We can ignore it. Now we look at the remaining peaks, and sure enough, in the aromatic region, we do see 6 carbons, 4 of them tall, 2 of them shorter, 4 CHs likely, 2 of the quaternaries, in this 120 to 140 ppm range. Very beautiful. The aliphatic region, sure enough, we do see our 2 peaks out here. No surprise there. The carbonyl, we see this one actually at about 152 ppm, a little bit lower than a standard ester, but you know, chloroesters is not the most common functional group we run across, so no surprise there. We see exactly the right number of carbons we would expect for FMOC, taking out of the picture the 2 we see for the solvent. And so now I'm 99.99% certain that our sample is FMOC. The chemical shifts worked out, the number of peaks worked out, in proton the integrations worked out, the coupling patterns worked out. This is FMOC. It's a wet sample, but it is, other than that, it is clean and it is ready to go. Critical information to have if you're going to use this in a long synthesis project, for example. So there we go. A nice illustration, I hope, of one of the more routine uses of NMR. We tend to focus on the big structural determination problems. They are great, but this is a much more common sort of thing we use NMR for. Check your starting materials. Make sure they are exactly what you expect them to be and that they are pure. Water is a common contaminant. If we had synthesized this molecule and we recrystallized it from acetone or hexane, we would almost certainly see a trace of that solvent in the NMR spectrum as well. Solvents from previous steps will often show up unless you are rigorous in your drawing. Fourth, chromatography solvents will show up sometime. So just be on the lookout for these things out there. Check your starting materials. It can save you so much hassle in the long run. Hope this helps, and we will talk to you later.